Cześć. Tak jak wspominałem w poprzednim odcinku, dziś będzie trochę trudniej, ponieważ wchodzimy w temat działania mikroturbiny. Ale spokojnie, jeszcze nie wyłączajcie filmu, ponieważ zaraz oddam Was pod skrzydła bardzo dobrego mechanika, który wszystko wytłumaczy Wam jasno, prosto i klarownie. Człowiekiem tym jest Halley, główny inżynier mechanik projektu, który był w nim od samego początku. Potrafi rozłożyć turbinę na dosłownie pojedyncze śrubki, o czym zaraz się przekonacie. Film ten otwiera cykl, w którym będę starał się Wam przedstawić, jak działa mikroturbina w różnych aspektach. Zapraszam Was na mój drugi w życiu film dokumentalny.
When the sun is setting below the horizon, it is a sign for Halley crew that it is time to go back.
See you at the runner!
Most of the devices are turned off before the last man left the station. But there is the one device that it is constantly giving power for all experiments through the whole Antarctic winter when there is nobody at the station. And here the history begins.
So the Halley automation project was initiated in 2017, and that was in response to the first winter shutdown of Halley station. So in 2016-17 season, Halley was relocated from a site which was Halley 6 to the new site, Halley 6A. The reason for the relocation was because of the Chasm 1, a crack in the Brunt ice shelf which had started propagating. And they moved the station to a safe location, but at the same time a new crack had opened up in October of that year, hence it was called Halloween crack. And with the advent of the two cracks, it was at that point that the British Antarctic Survey decided that they weren't going to winter personnel on the ice shelf. And that was the first time that nobody was going to be at Halley since it was established in 1956. So that's over 60 years of data gathering, of science, from the meteorological records, the ozone observations, space weather observations, the radars, the radio receivers. It was the first time that that had stopped. And with no people there to maintain the equipment over winter, all of the science data gathering stopped, and that was that. So it's a huge gap. So the Halley automation project was established to address that issue. So Halley was not going to winter for the foreseeable future. So we need a solution to keep the science running throughout the winter whilst people weren't there. So hence the Halley automation project. And to power the science, we needed something that was going to be around able to provide power at the 15 kilowatt level. The Antarctic winter in Halley lasts for 9 months, so people typically depart around February, March time and don't come back until November, December. So we needed something that could power a 15 kilowatt load for 9 months completely unattended. The initial idea came from an engineer within BAS called Mark Preston, and that was carried forward by the head of engineering technology, which was Mike Rose, and a collaboration was started with the estates team. So Joe Medal was the electrical engineer who oversaw that. The microturbine was identified, the capstone microturbine, which is able to provide up to 30 kilowatts of power, so well within the 15 kilowatt average that we were looking at. So yeah, the project was started in 2017. A microturbine was purchased and it was placed into a container. That container was then shipped down to Halley in the 2017-18 season. However, not enough time was available to get it running, basically. So the decision to not winter was made in January 2017. It wasn't until April, May time that the funding was available to purchase the microturbine. And then it wasn't until September, August that a container managed to get put inside a container, and it was then put on a ship down to Halley. There wasn't that much resource available at Halley to work on it. And so in the end, that first season, it wasn't signed off to run. So Halley went through a second winter with no data collection for the science. And in the meantime, the project was opened up to a wider group of people, a wider group of engineers within BAS to work on it. And it's in that second season that we got it running. So that process was quite involved. That's when I became involved in the project as well. We purchased a second microturbine, which was to be microturbine 2. And we used that as our test bed for the installation at Halley. So essentially we practiced everything we were going to do in the UK on that container to make it operational and commission it. And then we came down to Halley and repeated the process.
The bulk tanks each contain 22,000 litres of Jet A1 aviation fuel. The turbine runs at about between 6 and 7 litres an hour. So over the course of a sort of 8.5, 9-month winter, should use about 40 to 44,000 litres. So in theory, it'll only need 2 tanks. So the other 2 tanks are redundancy.
I guess the big thing in those initial stages that we were really focusing a lot of resource on was the automatic refueling. So in all of BAS operations, whenever we do a refueling operation, there's somebody there by a pump or by a dead man handle to stop the operation if there's a leak or a fault. We were going to be refueling this microturbine right throughout the winter with nobody there. So we had to have lots of fail safes in place. So a lot of engineering and thought went into how can we have an automatic fueling system that's not going to spill any fuel anywhere or completely reduces the risk of any fuel being spilt.
This is the only automated refueling system that BAS operate. We had to put in a lot of extra safety measures. We had to put in anti-siphon valves in there, and we had to put anti-flowback valves in the container. And then in theory, if any of these lines break during the winter, we can only lose what's in the line, which we work out to be about 25 litres, something like that. The lines are supported on the catenaries. Another thing we put in place was put in a spring at the end of the catenary so that if it got stressed, it would actually stretch as opposed to snapping.
Okay, so...
Okay.
We are on another side of the wall.
Yeah.
Say. So here we have 4 hoses and 4 fuel pumps. Why 4?
So, again, with the redundancy, we have 4 tanks of fuel, of which we only need 2. Now, originally, we had 2 pumps and a series of valves laid out on the floor, and the valves would switch. And the 2 pumps were the one thing that was sort of a point of failure that was a little bit close to the bone, because the first couple of seasons we actually had failures of these pumps. Now, these are very, very reliable pumps. They're 1-inch Blackmer pumps, and we use them quite extensively on the station. They're usually pretty trustworthy, but we had a couple of them seize up because the bearings were improperly set from the factory, and they tightened up over the course of the winter. And then we saw 2 years in a row we saw a pump failure. So so we realized with 4 tanks, instead of having 2 pumps and 4 valves, which were essentially 6 things that could go wrong, we thought, well, 4 tanks, 4 pumps, and then each pump is responsible for the contents of each tank, and if a pump fails, it just switches on to the next pump, and our redundancy is actually increased, even though we've actually got rid of quite a bit of plant from in here. So it's also a lot neater, nicely stacked up, whereas the old valves and pumps used to cover the entire floor area right out to here. You'd be stumbling over them. So so yeah, I think this is a much better setup. We're also looking next year to put in an additional 2 pumps on top of the tanks, which can transfer fuel from one tank to another, in either direction. So even if we do lose one pump, we will not lose access to that tank. We can transfer it into its neighboring tank and then carry on.
I think interesting thing is also the filters. Yeah.
Yeah, 2 micron filters. Again, each pair of pumps links into a single filter. So again, if we see a blockage in one filter, then we've still got another filter and another 2 pumps we can use. However, these pumps are huge, absolutely massive. They're designed to take hundreds and hundreds of thousands of litres, and we have, 88,000 litres out there, so a maximum of 44,000 that can pass through each of these filters, and it's very, very clean fuel. We've just cleaned it today, made sure the tanks are clean, and it's a very thin fuel as well. So even if we did get huge amounts of water and debris, I think it would take a very long time for these filters to actually block.
Okay, so from here, fuel is going to this huge tank over here. It contains 2 tons.
That's right.
Of fuel. But in general, from here, the fuel going here, and to the microturbine.
And then if you come around the side here, you can then see its path. So through the inlet, it comes up, and through this is another 1 micron filter.
Yeah.
And then that goes up into what they call a cascon pump. This is the high pressure pump. And then it goes onto a fuel rail, and these are the solenoids that control the injectors. So you have 3 injectors.
3, okay.
And depending on the load that is put on the engine, it uses as many injectors as it needs.
So we have a fuel system. What is this?
So that is a dump valve. And what this does, it releases the pressure in the engine if it gets too much pressure.
Okay.
So it uses the pressure for a couple of things. Obviously, it has its the main turbine needs pressure to compress the air to deal with fuel ignition. It also, off the other side of this, so this is literally taking air pressure out of the engine. Off the other side of this, you've got these pipes that go to another manifold back there, and that comes up to the other side of the injector, and this is the air assistance for atomizing the fuel. So up to 7 kilowatts, it uses this compressor here to put in additional air to atomize the fuel. Over 7 kilowatts, it has sufficient pressure to actually operate its own injectors. Then, so it just uses that air pressure, and it blows it around the injector head. So you have a single fuel nozzle in the center of the injector, and then you have a matrix of air holes that are surround that, and as the fuel is squirted out, the air crosses its path and atomizes it, essentially. So that, going back to the dump valve is actually out here, located here, and what this does is, if you have this operating flat out, so the maximum operating speed of this is 96,000 RPM, And
Yeah.
that's what it's working at if you've got it fully loaded up, sort of 25 plus kilowatts. If you then suddenly release the load, if you take the 25 kilowatts away, because of the heat that's in the engine, it will start to self-accelerate, and it has no way of slowing itself down because you've taken the load off the alternator. So the only way it can actually slow the turbine down at that point is to open that valve and directly let the pressure in the engine out into atmosphere. And it is quite interesting when it happens. The battery control unit is this massive unit here, and what that does is it talks to the battery pack.
Because we have a battery pack in general here.
There we go.
That's battery pack contains
18.
12 volts batteries connected in a row.
That's it, yep, up to about 220 odd volts DC. And what the battery pack does, it first and foremost, it's used to start the engine, and it's used to cool the engine down. So when it comes off load, it turns its alternator, which is here, the main generator portion of the engine. It turns that from a generator into a motor, and it runs the turbine to cool it down. It also runs the turbine to do its initial lift off. But what the battery pack also does is it controls the spikes in the power demands. So if you're going to start from the start, so you have an AC generator here. The AC generator then goes down to the main power control unit, also known as the DPC, and the DPC converts the AC current coming out of the alternator into DC current, and it turns it into 760 volts DC, and then it goes through another set of inverters that turns it back into AC 400 volts going out to the main supply. And that 760 volts DC bus, as you get high demands of power coming on, that will fluctuate, and the engine will take just a few moments to speed up and to cope with a sudden power demand, and the batteries compensate for that. And that's why it has this huge battery control terminal which communicates constantly with the batteries and uses the battery power to support the DC bus, which is put through that. So yeah, as we say, we have the battery control unit. We then have the main power control unit. This operates the engine, and it operates all of the power generation side of it. This doesn't have any thrust, but it only has a single moving part through the middle, which is a compressor shaft. So so the shaft runs through the alternator with the armature on it, and then it goes. It has an impeller on it, and then the impeller draws the air in, and then it has a compressor that compresses the air, and then on the way out of the combustion chamber, there's a turbine. So when you have the impeller compressing the air, it goes through a heat exchanger as it's compressing, and then it goes into the combustion chamber, which is right in the heart of the engine, around in this area. You can see these injectors, these 3 injectors, they all point straight into the middle of the core of the engine, which is where the combustion chamber is. So you end up with your air heavily compressed in there, and then your fuel goes in and is ignited. As it leaves, it drives your turbine, just like a turbocharger, and then the hot air or the hot gases go out through the heat exchanger and then exit through the exhaust, which is back at the front of the engine. And that's basically it. So as I said before, it uses its exhaust temperature here to regulate how much fuel it puts in. That's what it uses. It sets the temperature on that, and then it knows what the temperature should be. If it's less than that, it puts more fuel in.
So in general, it doesn't care about the load. It
No.
cares about outlet temperature.
That's it, yeah. So the more you try and slow the engine down by increasing the load, the cooler this will become,
Yeah.
and the engine will see that and say, right, I need that to be hotter, and it will put more fuel in. So it doesn't really matter how fast it's running. So when it comes on load to start with, it idles at about 46,000 RPM, and it tops out at 96,000 RPM. And it's not worried about whether it's doing 45 or 96. All it's worried about is keeping that exhaust temperature. The speed of it is almost a byproduct. And then because of the electronics in here, converting the energy, most alternators, they want to run at a set speed. This one, it just goes whatever speed it wants, and then this deals with the energy coming out, changes it to DC and then back to AC again. And by the time it's coming out, it's as smooth as silk. And you can alter the voltages, you can alter the frequencies, set it to whatever frequency you want. I mean, one thing we've seen with the microturbine is fuel efficiency, like per kilowatt hour, is not as good as on a standard sort of reciprocal engine, as they call it, a piston engine. I mean, at the moment, the big engines up on the main platform that are running, it costs us about 1/3 of a litre to produce 1 kilowatt hour, whereas this takes 1/2 litre to produce 1 kilowatt hour. So there is sort of like this kind of this fuel efficiency issue that you say, well, we are actually using more fuel to get your energy. But, and this is the key, this is what separates it from every other engine we have on this site. So we spoke about the single shaft that runs through the middle, and that single shaft runs on these foil bearings. And again, that compressor that's in there, that's creating all that air pressure that it uses for its injectors and whatnot, it also feeds that pressure back into the foil bearings. So once the compressor shaft is going more than 2000 RPM, it starts to create its own cushion of air. And then this rotor that runs right the way through it just spins on this cushion of air. There's 3 bearings altogether, and once they're up to speed, there's virtually no contact and there's virtually no wear. So that means that there's no oil, there's no lubricant. So again, going back to our engines here, we would run that for about 250 hours before we have to change the oil. You can get away with doing 500 hours and then changing the oil. You probably won't see too much detriment to that. This thing will do 40,000 hours on the bearings it has. So if you start to look at the other things that need to be changed, the other service items, so they recommend you change the injectors every 20,000 hours. And they recommend that you change the fuel filter every 8,000 hours. So that was our smallest number, the fuel filter at 8,000 hours. And then we fitted a bigger one, which meant that actually we could do nearly 20,000 hours on that.
Whilst we were still in Cambridge, we knew we were going to come across one big challenge. And this has been the biggest challenge of the entire project to date. So we're into year 6 now of the project. And that is the heating and cooling within the container. So we knew in Cambridge that the turbine was going to produce heat, and we needed it to keep it at an ambient temperature level. We needed to get rid of that heat, but also not let it get too cold. Now, in Cambridge, we weren't able to test that because we didn't have Antarctic conditions. We considered putting the container in a test facility where we could reduce it down to -50 conditions and properly test it, but that was going to be costing the organisation a few £1 million. So we didn't go down that route. And so we had to learn as we went when we got down to Halley. So, and that was the biggest challenge.
That's where we come back to the bigger picture, isn't it? You know, so you've got the turbine here, but then the rest of the container is here to support the turbine. So as you spoke about earlier, Seb, we have a large heat exchanger. So the exhaust that runs out goes through this tube. This tube is hollow. and then it can use this tube to induct fresh air into the container, that because it passes by the exhaust pipe, it gets hot. So we can bring in outside air that is above ambient temperature. How much above ambient temperature depends on how long this is. And originally it went all the way to the turbine, and the temperature at which the air used to enter the container was so unbelievably hot that it would only last about 2 hours before it overheated. So we cut down the heat exchanger and we installed that fella on the door, which is what we're what you're working on now, isn't it, Seb?
Yeah.
So you've got the air handling unit. I presume you're going to talk more about that another time. But
Yeah.
that's pulling fresh air into the container when it needs it. Which means this is the only thing that you could leave down here for 9 months of the year without anybody here, and it still be running when you came back. If it was a standard recip engine, it would be in pieces. It would have thrown its guts out all over the floor.
The challenge for me was bringing lots of different departments together, lots of different knowledge bases, and producing it into one product and making that work. What I've found is that different engineers and different disciplines, they often speak different languages. So mechanical engineers speak a different language to electrical engineers, speak a different language to electronics engineers, and speak a different language to IT engineers and data managers. And there's a lot of complex terminology that goes on that to manage was quite difficult to process, because you need to learn a little bit but not waste time learning all of it. And you need to be able to communicate that knowledge between the different departments and go, no, that's not what they mean. They mean we're doing this. Oh, no, that's not what you mean. We mean this. So that's probably one of the biggest challenges. But that's also probably one of the most satisfying and joyful parts of the project, I found, because you're bringing together all of these brains. There's a fantastic amount of knowledge in all of the different engineers and people that are working on it. And you're learning things about electrical systems, about mechanical systems, about engines. I didn't have a background in jet engines, and now I know a little bit more about it. So that's both the biggest challenge, but also the most satisfying thing about the project, I would say. And that's the fun part of it, which when you have the engineers all agreeing on one solution and one way forward. Because that was often my own sort of joke. It was, we're trying to find a solution, and I speak to 4 different engineers and I get 4 different engineering solutions. And I'm trying to make a decision on which is the right one. But when we're all on the same page, then it really works. It works really well.